I'd say, yeah, so some of these you can definitely eliminate. It's going to also, if you're starting to kind of the influence quantities, first thing you're going to look at is basically your tolerance on your drawing. You know, if you have a tolerance of 100 microns plus or minus, or 50 microns or something like that, okay, your instrument's probably okay, you can eliminate that. You can probably say your workpiece, if there's a high throughput and stuff, you know, it's probably a pretty good manufacturing process. Probably eliminate that. The things you really want to measure, worry about, you can probably eliminate the measurement strategy if you're going to do sampling or anything of that nature. The things you got to really worry about is now your environment and then your extrinsic stuff. Stuff you really can't control, you have a really hard time controlling. And these things are always going to be inherent. Anything that's environmental, it's always going to be inherent. The best way to kind of eliminate this is, okay, if you try your best to control, and you're not a temperature control, but you do your best to try to control your temperature, because that's probably the biggest issue is thermal errors. One thing to do is kind of, as I mentioned earlier, kind of have a test piece, a test part. You measure X amount of parts, put your test part in, check it, measure it again, and then now you can kind of look at a bias. And within that bias, you're hoping that those errors from the thermal errors are manifested into that data. That's your best way of quantifying that without having to go in and actually thermally correct everything. And that kind of gets kind of tricky real fast. That's not fun. Okay, so a little bit about our design strategy. So what we kind of did is we inventoried our CMMs and our sizes. And we're calling sizes, we're talking our measurement volumes. So this is kind of the way we went ahead and estimated these limits based on the machine spec. So this is kind of an example. We have a PMMC. So this is a type of CMM by one of the manufacturers that is a moving table CMM. So I won't get into too much detail. But the head is rigid, so then we basically get rid of dynamic errors on the head from an articulation. So these are some of the manufacturer specifications that are given to us. So this MPE is a maximum permissible error. In other words, this is the maximum error for this particular test. P, we're calling probing. S, we're calling scanning. L is our length, basically our radius of our machine checking gauge radius. And then we're using our size equation, which we call our MPL. This is basically from the 10360-2. And then another thing we're looking at is a B89. So the B89, B89 4.4 10360-2008, I believe. It has an additional pivot repeatability test. So we're actually using it also because of the fact that this MCG sits on a pivot. And we're looking at some of the repeatability. So for the PMMC, we have a plus or minus. So basically, this is our MPL. So this equation is pretty standard for any CMM that's calibrated. Basically, here you're looking at the variance of your repeated measurement on the final dimension. Here, this is your length, your value, your diameter, your tolerance, your distance of your tolerance, your true position tolerance. Anything that's related to length, that's plugged in here. And this right here is what we call our length-dependent factor. And basically what it is, in essence, is when you plug this in and you calculate it, you get your maximum permissible error for length in micrometers, in scans law. This is all dependent on this L equation. All these equations differ per machine. The more accurate the machine, the smaller this variance number is going to be, and probably the smaller this number is. The larger machine, the less accurate, the bigger. So basically what we did is, okay, now we looked at tolerance estimation. So now I'm going to try to explain a little bit on what we're doing here. So right here, when you're using a machine checking gauge, basically what it does is it generates this large sphere, simulates a large sphere like I mentioned. So basically what we're doing is the CMM is tactically taking points at 3 different levels at 45 degrees. And I'll get into that in the next slide. But basically we're trying to estimate, okay, this is our estimation of our tolerances. So now we're looking at 2 times the MPE of the length. And the reason we're doing that is because of the plus or minus. So we're adding them together, in essence, adding them or multiplying them times 2. Plus, so in quadrature, adding in quadrature is the probing, the tactical probing. This is our specification from the manufacturer. And basically what we do is we estimate a tolerance. So this, for our sphere form, anything that exceeds this isn't gonna, basically is out of tolerance. We can't use. So every measurement we take, we're assuming that it's got to be smaller than this. We're hoping that it's smaller than this. If it's something bigger, then we know something, it's a red flag. It's an outlier. It's telling us something's wrong. Similar for the scanning, so the MCG isn't really made for scanning because we have a lot of issues that is inherent in dynamic scanning that's not the same with tactical probing. But in essence, we're doing the same exact thing, but now we're taking the manufacturing spec for scanning. So anything that's 4 microns. So again, this is for our PMMC, one of our CMMs. And the pivot repeatability, in essence what we're doing is we're taking that B89 value that's from the standard and we're multiplying it by in essence, a safety factor. I don't want anybody to get confused and assume that we're using this as kind of a confidence interval for 95%. But basically what we're doing is we're assuming, okay, let's multiply it times 2. In a sense, it gives us, okay, if it's anywhere in here, we're good for our pivot repeatability. So this is kind of ties in now to our design strategy, okay, and I was mentioning this. So what the MCG tells us is basically we're looking at point-to-point collection. So here at 3 different levels, we have 0 degrees and plus or minus 45 degrees. And at each level, we're taking 8 points. And from there, we get a total of 24 points. This is straight from the manufacturer and the data collection recommended by the manufacturer. But what we do at Los Alamos, since we do a lot of dynamic scanning for a lot of our parts, because we do a lot of high data density on a lot of our components, we figured, okay, let's try collecting some scanning data using this MCG. But first, let's try in the XY plane at 0 degrees with 4 scans. The reason we do that is because once we go up to plus or minus 45, now we have issues with anything that's inherent in dynamic scanning errors. So now we're worried about, is our direction vector there? Are we getting a lot of errors from our direction vector? Is it matching up? Is our radius going to be the same? Another issue is that now we're kind of worried about this kinematic C here. If this kinematic C isn't above the center line here, then it won't trigger a point. So we may have lots of data. And then if the machine's moving too fast, we won't get any measurements from, as I mentioned, from the probing vectors, from anything that's dynamic in the errors. So we're testing this out. We're going to see about going 3D on this with a sphere. And they kind of, with the user manuals deviations, kind of stylus section, they suggest certain stylus, probing, and scanning. And here's kind of what our sample size is. We're talking about sample size, how many measurements you want to take for, and we're basing this off of our desired margin for error. So basically, we can calculate this using as a quantity squared of the z-score times the standard deviation over the margin of error. So basically, if we want to look at 95% confidence with a margin of error of 1 micrometer, we're looking at approximately 9 measurements. If we want to look at 99%, with the same margin of error, we're looking at about 14 measurements. Now, if we cut that in half, we're going submicron, we're looking at 500 nanometers, and we want to look at 95%, now we're looking at 33 measurements. Similar for 99%, now we're looking at 56. So you can see the smaller the margin of error, the larger the number of measurements you need to collect for our sample size. Well, since we don't have that much time to take that many measurements, and just kind of doing a little bit of expert judgment intuition, 20 should probably get us through a micrometer or sub-micrometer margin of error, 20 measurements. And at 20 measurements, that should really tell us whether our distribution is going to be normal or not. So that'll kind of help us out. But this is kind of the strategy we're using for our sample size. So I'm actually going to pass this on to Josh, and he's going to talk a little bit about our procedure and how we go about performing these interim checks there in Los Alamos.
All right, so I missed the introduction, I think, earlier, but I'm Josh. They're the brains, and I'm the old guy, I guess. I don't know. But the procedure. So we want to hear it. What was that?
We want to hear old guy.
Yeah. The procedure. We decided to put a little procedure together because I don't know. Up at our place, we have a pretty wide spectrum on our staff. A lot of our inspectors, some are very inexperienced, and we have some that have been there forever, and like journeymen, and not operators, they're inspectors, and it's an art and the whole bit. But to level the playing field, we put a procedure together. The other thing, we're rolling this product out in 3 different labs. We're in our depleted uranium shop, our beryllium facility, and there is our stainless steel where non-hazardous work happens. We're yet to roll it out in our HE facility and plutonium, some other sites, but that's soon to happen. But basically in the procedure, it's basically a little work instruction.